Hi guys, in this video we are going to talk about the different assumptions. So first of all, the model here without Finland only explains 70.9 it's 97, let's say, percent, almost 70, almost 71% of the variance of the sales per capita of computers in US dollars. Okay, so this is the number one here. The number two, we are gonna take a look here very quickly. It's less than or equal to 0.05, which means that all variables in the model are important. However, are they significant? This is another question. Before we get there, we need to take a look at the two standard errors. We already done that, right? Because we, here's the standard error, right? So, let's do it very quickly in order. So over here, we're gonna have to say if the absolute value of this guy here is less than or equal to the this value. What happened? If this value, the absolute value, is less than or equal to D25, right? D25. Give me one else, give me a 0. Sorry guys, I have extra. Nani? Where is if? If this, the absolute value, and here we go. Now, what I usually tell you to do is to put the absolute value before the residuals, right? Because right now we are gonna look into the homoskedasticity assumption. So let's be consistent right now and take all this together and move it a little bit and put here the absolute residuals, because this will help us, right guys, later when we do the homoskedasticity. In any case, you can keep this as is right there, and now you have only one value, so you could say that up here for the standard error you could say something like how many values are within two standard errors. So you say the sum of all these over the count, which is here, the count is the number of observations, which is 20. So 95%, so you can put it as a percentage. You can say 95% of the data points lie within two standard errors. Okay? All right. Now, over here, we are going to delay. Let's say they are all less than 0.05. And we say all variables, here variables as independent variables, are significant given the model meets all linear regression assumptions, or satisfies, given that the model satisfies all linear regression assumptions. Good? Perfect. Okay, now let's take a look at these coefficients over here. All right. Now, let's get started. We're gonna take a look at the normality assumption of the error terms. And with this, we're gonna find the skewness and the kurtosis. So basically, we're gonna take a look at skew for the residuals. And we're gonna take a look at the kurt. So, ne? If you guys remember, we had that table. As you can see here, our sample is 20. So if the skewness is in within these bounds, which it is, then it is normally distributed. Because here, let's take it. How about we copy that? Let's copy this. It's in the slides. And this is here, make it smaller. And over here, you see 20. And the skewness is 0.8, it's in within. And the kurtosis is 0.1, it's also in between. So there seem not to be any violation of the normality assumption of the error terms or of the residuals. Good. So this is number one. Number two is the homoscedasticity assumption. With the homoscedasticity assumptions, lovelies, we're going to start with the visualization. As you guys remember, visualizations is basically these guys with these guys. So we just take it. These guys is the dependent variable and the absolute errors. So we take them like that. And now we take a look here. How about we say here homoscedasticity visual check. How about that? Yeah. And over here, as you guys know me already, I like to make sure just very clearly I see that these are the values 100 something. This is the dependent variable, right guys? So I'm gonna here on the x-axis put the dependent or sales per capita. Yeah. And over here is the absolute residuals, right guys? And now we are going to, let's get rid of this, it has no meaning here. And we are going to select one point and add a trend line, and it should be linear. And we're going to display the equation and the R, and this is it. But because we want to take a quick look at them, we are going to move them a little bit where we can see them. Not the whole thing, just these guys. Let's take a look here. R square is 0.1. And this is a linear model with 0.15 as a coefficient. Seems like, let's see. This is here, I would say it seems to be, there seems to be a certain behavior here. As the sales per capita increases, maybe the absolute error kind of, I'm not sure, this because it's closer, this is farther. It seems to be increasingly more. I suspect that we won't be faced with homoscedasticity. Let's do I think we will, the Prussian and Pagan test of linear homoscedasticity. And this test, we are going to take the squared residuals. Do you guys remember that? So we're going to take the square residuals. For this purpose, we're going to take the residual, multiply it by itself, right guys? And then we are going to do it like that. And then we are going to go to data, and we are going to get another regression model. In this regression model, we're going to take the square residuals to be the y value. Why don't we take the label? Yeah, let's do that. And then the independent variables as is. Where are the independent variables? The independent variables come from a different data set over here. So the independent variables are these two guys here, right? And we don't need the residuals for this test. And then let's put the output not in a new sheet. Let's keep it here in our sheet, right under where we are checking the assumption. And now this is here with y being square residuals and regressed against the independent variables. Okay, guys? And now we are going to get the chi-square statistic. And the chi-square statistics is basically chi the chi-square statistic here is basically the r square times the number of observations, right? And now the p-value, oh sorry guys, the p-value of this r statistic is chi dot or chi-square dot, was it dot invert dot rt or dot distribution dot rt? Probability and degrees of freedom. Now we know which one it was. So let me check also. Do I have a Prussian? Okay, I don't have the slides here, but I will provide them to you. So this is for the Prussian and Pagan test. Before I terminate this video, I'm just gonna just make sure that I don't give you any wrong information. I just need to make sure that I exactly give you the right information. I kind of sometimes these days I'm not really very much focused. So the chi distribution RT, that's correct. So this is what we need. Anyway, the chi invert, it won't work. The chi distribution RT is the right one. The chi invert won't work. So what does that mean? This means it's greater than 0.05. So apparently I was wrong. So even though I was telling you, visually I see a linear function here. This is why we need the Prussian Pagan test. So over here, this linear function isn't as influential. So over here, we accept the null hypothesis of no presence of heteroscedasticity. Because always the null hypothesis is no, there's no heteroscedasticity. So we want to say yes, there's no. If we reject it, this means yes, there is heteroscedasticity. So there is no enough evidence. There isn't enough evidence of the presence of heteroscedasticity. All right. Very good. Now we go to the multicollinearity. With the multicollinearity check, it was a habit that we start with the correlation, and we check the correlation among the independent variables. So these two independent variables, we take them and we take their labels and we take the output maybe to be here. Sorry. Take the output to be here and okay. And since we have only two variables over here, we can say the R square is basically, this is R. This is the Pearson correlation R. But R square is this. So this would be R square. And this we can do it here this way because we have only two variables and two variables only. Yeah. So in this sense, this is the R square and the VIF would be as follows. 1 over 1 minus this, and this value is less than 3, and we say there is no evidence of multicollinearity. If this method is confusing you, the standard method that we do is as follows. We use one of them as y and one of them as x. So we take regression and we say okay, and we say the y is one of the independent variables. Let's say it is this one, and the x is the other independent variable, and we take it to be this one, and we take the labels and we take the output here to be somewhere here, let's say. Okay, and then we say okay, and as you can see, this is R square. Is it the same value? 329. 329, exactly, it's the same value. And then you take the VIF and you say the VIF is equal to 1 over 1 minus this R square, and this is it, 1.49, which is almost 1.5, 1.49. So this is how we got it, and this is the way that we do it. This way is a must. This method is a must if you have 3 independent variables or more. So this method is a must that you need to run linear regression from the analysis tool pack if you have 3 linear independent variables, 3 independent variables or more. But if you have 2 independent variables, as you can see here, this method with the correlation matrix and then just taking the square of the Pearson correlation will be just sufficient. Then you can get the VIF easily. And as you can see, since the model satisfies or meets all the required assumptions, yeah, there the coefficients of the independent variables are validated. They are the significant coefficients. The significant coefficients of the independent variable are validated. Yeah. So now we can say with much confidence that what happened here? There's nothing showing over here. So a 1 unit increase of GNP per head will yield 0.0017 increase in sales per capita. This is what you were right? Per capita. Let's see what we have in the slides. We are not there yet. This is the Prussian Pagan test here. So I'm going to put this kind of set of slides on the Moodle. And computer spending examples for European countries. This is the skewness and the kurtosis. Non-normality of residuals was met. Oh, they were not normal? Non-normality of residuals invalidates the p-values that you used to determine significance of independent variables. So what do you do if this is invalidated? I'm going to give you an example. What to do when the normality assumption is invalidated. So the normality assumption is invalidated. You need to transform the dependent variable. And the way to transform the dependent variable, you can take either the natural logarithm of y, the square root of y, or you take the inverse of y. So that might resolve the non-normality of the errors. But for now, guys, it's okay. I am going to give you these special cases. Special case 1, what happens if the normality assumption is invalidated? What happens if this is invalidated? What happens if this is invalidated? So I'm going to give you examples. But for now, this is all right. Do I have the results here? Testing validity. Over here. This is the Mao Palace, is it? No. This is a different, this is also something that I wanted to talk to you about. This is for the sales data set. I should have put it before I ran here. Now you might think 1 unit, but actually it is measured in billions. So a billion increase in last quarter's GNP increases quarterly sales by 174. So this value here, you might think that this is a very small value, but in fact, you guys, these units, I did not explain. In fact, it's my fault. I did not explain at the very beginning, maybe, but this is in millions, the sales. So the sales per capita in million. So, and this is in also in million. This is in percentages. So this is how, based on the results here, let's see if our results are similar to their results. We got 174, I hope. 1723. They got 174. Maybe some a little bit of discrepancy here and there. But over here, they have different quarters. This is for quarterly sales. I'm really sorry. Where is the Europe one? What's happening to me? Here. This is the Europe one, finally. So this is the Europe one. So here's the data exactly like ours, 001723. So basically the linear model is as follows. Here, what is your linear model? If I ask you, what is your linear model? Your linear model is minus 38.48 plus 0.001723 multiplied by GNP per head plus 15.31 multiplied by the percentages. So this is your linear model right there. I'm sorry, guys. So this is the linear model right there. Okay? The equation explains, the author focuses on R square. I focus on the adjusted R square. I am more correct than the author. So the author focuses on this. I focus on the adjusted R-square. You need to focus on the adjusted R-square, not the R-square alone. Because the standard error is this, you expect 95% of the forecast to be accurate with 58.26, within 58.26 standard errors. From the residuals portion of the output, you can see that Switzerland, as you can see, is the only outlier. After adjusting for a fraction of GNP spent on education, a 1,000 increase in per capita GNP, you see. Now, one of my students asked me, why do we always say 1 unit? Yes, we say 1 unit, but depending what is the unit. So over here, the unit in our case, we adjusted it so that we can, it's 1 unit increase, as we wrote here. You write correctly. You said a 1 unit increase will yield 0.1723 increase in sales per capita. To make this a little bit more readable, you multiply this by 1, 2, 3. And you multiply this unit by 1, 2, 3. So it becomes a $1,000 increase in GNP per head yields $1.723 increase in sales per capita. So if you multiply both sides by a certain number to make it more natural, yes, you can do that. So if you are presenting your research, your thesis research or whatnot, this is really like, it looks trivial. It looks a little bit not natural. So this is, we're talking about population, nations, millions of people. So it's okay if you say a $1,000 increase of GNP per head will yield $1.72 increase in sales per capita. So over here, you can transform this into the following. $1,000 is spent or increase in spend of GNP per head yields let's put the dollar sign, $1.723 increase in sales per capita. So that is awesome, isn't it? Right there. After adjusting for per capita GNP, of course, you always need to say that because you have, you know why? Because you have more than one independent variable. This is not simple linear regression. So we always have to say keeping other variables constant, or after adjusting for a fraction spent in blah, blah, blah. Depending on, you should be an expert in this area so that you can write it really nicely. So IR students, if we have any in this course, they might find it natural to speak in the language that I've just written right now, because this is how they speak about spend in GNP, blah, blah, blah. But for you, you're not an expert in this area, so I'm fine with it. The same applies over here. You might need to multiply by 100. So let's take a look. After adjusting for capita GNP, a 1% increase in the fraction of GNP spent on education yields $15.31. So this is, in fact, the $15.31. So this is natural as $15.31, not like the other one. The other one was a little bit unnatural, and this is how we deal with it. I'm really sorry for extending this video unnecessarily. I should have opened up the... I was looking at other slides to see what we're going to do for next Tuesday. I really apologize for this. I hope that you've been able to just move forward until you reach to this point. So this is the end of our investigation. So today we have learned a lot. We instilled and remembered how to do all this together. We learned that there are two methods for multicollinearity. This method is easier when you have only two independent variables. And the method that we've learned earlier in Mao Palace with this traditional classical way of doing things is a must when you have 3 independent variables or more. And also we've learned today how to make the very difficult decisions of getting rid of outliers. Are they influential outliers? So today you've learned something new called influential outliers, highly influential or not highly influential outliers. You also learned today how to adjust a little bit the units over here so that you make it a little bit natural when you're interpreting your results. You also, what else do we learn? We are going to learn in a Tuesday more interesting topics. We're going to learn what to do when this assumption is violated, what to do when this assumption is violated, and so on. Mostly, we're going to learn what to do when this assumption is violated, and also hopefully we can talk about moderation effects as well. Thank you so much for today, and I hope that you will finish up all this assignment and submit it on Moodle on time. Take care of yourself, and I'll see you on Tuesday. Goodbye.